Hi everyone, welcome back. This is our second video, and here we'll start the steps of proving Theorem A. So recall, as I said in the end of the first video, the starting point of Theorem A is this observation that positive scalar curvature implies smallness of certain kinds of minimal surfaces on the ambient manifold. So our strategy for proving the theorem would be to first show that, and then decompose the manifold into cutting it along several of those manifolds, and then obtaining a lot of connected components, and then trying to extend this smallness to propagate them to the interior of those components, and then obtain a singular kind of foliation that would give us our desired graph, gamma, and the map. Okay, so I want to first start recalling some sort of basic facts about minimal surfaces on three manifolds that would allow me to introduce this result about the geometric smallness of those surfaces, and then we'll go into the construction of them, and then the cutting procedure of them, and then finally we'll go into the work of propagating those bounds towards the inside of the manifold. Okay, so let's start with the basics here. I'll just recall some facts. So if I have a minimal surface on the three manifold, and I want to look at some certain variations of the surface that are of this kind, like a function phi times the normal of the surface, so just a perturbation. And what we'll do is we're going to calculate area along those perturbations and take a derivative at t equals 0, which is the surface sigma itself. And when we do that calculation, we get this integral expression, the integral of the surface gradient of phi squared minus, this is the Ricci curvature in the direction n, the normal direction, plus a squared times phi, and a here is the second fundamental form. So you can see this if you never looked at this expression before. You can think about it as a natural extension of the calculation along geodesics. So when we have a geodesic along a manifold, and you look at the second variation of energy, you similarly get a square term here of a derivative, and then minus a curvature term. And one can think that these applications of minimal surfaces, as Shannon and Yao started using for scalar curvature, are natural generalizations of the theory of geodesics that people used in the 40s and 50s and 60s to study curvature. So it's a very natural extension. It's a more powerful tool actually, because when you're dealing with geodesics, you look at the second variation of geodesic, you're sampling just a small space of the ambient geometry, whereas in the surface or hypersurface, you vary that. It has a lot of information about the ambient geometry in the neighborhood of that surface. So, okay, and what does stability mean? Well, stability is basically that this integral quantity is greater or equal than 0, no matter what variation phi you choose. So that's what it means that the surface is area minimizing up to second order. Okay, and whenever that happens, well, you can integrate this grad phi squared here, you integrate this by parts, and you get a term like phi, Laplacian of phi. And the conclusion is that this operator, which is an operator over the surface, Laplacian plus Ricci in the normal direction plus a squared, has no negative first eigenvalue. Okay, so that's what stability means. And what is the connection with scalar curvature? Well, the connection is that if I take the first eigenfunction for this operator, we call that a function u. So that first eigenfunctions of operator of this kind, they're always positive. So I can then look at this following metric here on sigma, which is u squared times g, where g is just the restriction of the ambient metric over sigma. So if I look at this, this is going to be a metric, a conformal metric, right, to the original one that I had on the surface. Well, this conformal metric is going to be a metric of positive Gauss curvature. Okay, so if the ambient has positive scalar curvature, and I look at a minimal surface, then that minimal surface also admits a metric of positive scalar curvature. In this case, the dimension is 2, so it's also positive Gauss curvature. So that's the fundamental connection that was found by Shen Yao. So in particular, what topology in sigma has, well, it can only be a sphere, because or else it wouldn't admit a metric of positive Gauss curvature. Okay, so this is how that fundamental observation of Shen Yao is actually proven. Okay, so this is the sort of basic background to show the geometric smallness. So the theorem that's going to be heavily used on the rest of this talk, it's the following. So that if I have a lower bound on scalar curvature, a positive lower bound, then for stable surfaces, I get a positive. In the case where I have boundary, then I can bound the distance from my interior point to the boundary. This has to be bounded by at most 2 pi over root lambda. In the case when the surface doesn't have boundary, then I actually, theorem A, just this basic application of part A, give me that the diameter has to be bounded from above. And when sigma has index 1, and also no boundary, then I actually get slightly larger, but still I do get a diameter bound. And let me just illustrate how you can conclude that diameter bound from part C by using part A. So let's say we have a minimal surface here of index 1. So interested in looking at its diameter. So let's consider points here, P and Q, which are the furthest apart, let's say. So I'm going to start looking at, say, here, this point, and let's start looking at geodesic balls. So this is the ball of radius, geodesic ball of radius R, centered at this point here. Now, whenever I decompose a surface like this, which has index 1, in 2 pieces like that, then one of them has to be stable. That's basically what index 1 means. So if I decompose in 2 parts, one has to be stable, because if both were unstable, that means that you would have two directions, independent directions where you could decrease area. But in the index 1 minimal surface, there is essentially only one direction. Another way of saying that is that in the index 1 minimal surface, when I look at that operator L, I have only one negative eigenvalue, and all the others eigenvalues are positive. Okay, so in this picture here, because this guy is the smallest one, I can say for sure that this is going to be the stable one, and this is going to be the unstable. Now, what I'm going to do is I'm going to start increasing this ball. And what happens when I do that is that this is still stable, but the eigenvalue for the operator L restricted to this domain is decreasing. It's decreasing, decreasing, decreasing until it comes a point when it has 0. So right here, let's say that the lambda 1, it's 0. Okay, so that means that if I go slightly over, so if I go, let's say, slightly over radius, then the first eigenvalue now of this domain here in the surface, it's going to be negative. Okay, so it means now that this is unstable, you see? So that must mean that this other piece is stable then. Okay, so basically what I do is then I say, okay, so this is stable. I can apply then part A to this piece. And then I apply part A also to this other half just before I get in. And then basically I get that this distance from this point to this point is at most 2 pi over root lambda plus 2 pi over root lambda, which is 4 pi over root lambda. Okay. So essentially, the geometric smallness that we're going to use, it's all embedded in this statement of part A. Now, how do we actually prove part A? Well, the proof of part A basically comes from that observation from the previous page. Because when I have a stable surface, if I look at u squared times g, if I look at this metric here over the surface, well, remember when I said in the previous slide that positive scalar curvature implies that this is going to be a metric of positive Gauss curvature on the surface. So, but if you actually have not just positive scalar curvature, if you have a lower bound like positive, scalar curvature bigger than lambda, then you can show that this guy is going to have a positive lower bound on Gauss curvature that depends on lambda. So you can apply the Bonnet theorem to this metric, and then you can bound distances or diameter of this metric. But then, of course, we want a statement about the metric, not this conformal metric, but we want a statement about the metric just G. So basically what really goes into the proof of theorem A is that you can do that. Somehow you can estimate this conformal factor in some fashion and then end up with a result for the metric G. So again, a lower bound in scalar curvature would say that of the ambient would say that you have a lower bound of Gauss curvature for this conformal metric, and then you can apply diameter estimates, right, for this conformal metric, but you still have to go from that to your original metric G. So it basically comes down to controlling this conformal factor U in some sense. But that's how you obtain this diameter estimates. Okay. Now the other geometric smallness that we're going to use comes from this result here of Yao and Marcus and Evis. So which basically says that you also can estimate the area of a stable minimal surface from above and again index 1. Okay, so the proof of this, I'm not going to go into it, especially the index 1 case, because you have to use a trick there. But basically the idea is you go back to that second variation, that integral form, and you cook up interesting test functions that will allow also that once you plug them in the integral expression, you can make conclusions about the area of the surface. Okay. But all right, so I'm going to assume then that we have covered the geometric smallness of these minimal surfaces. So now let's go on decomposing our manifold, like finding them in our manifold. Okay. Oops, it seems that I have to get rid of this. So let's see clear. All right, let's go. Okay. So given a manifold M now with positive scalar curvature, first I'm going to look at, I'm going to make a small technical assumption, which is that I'm going to assume that that manifold that with that positive scalar curvature metric is bumpy. So what does that mean, a bumpy manifold? Well, basically the bumpy manifold, it means that all my my surfaces, right, don't have Jacobi fields. Okay, all my minimal surfaces don't have Jacobi fields. So Jacobi field would be a function phi, which is an eigenfunction for that stability operator with eigenvalue 0. Why I don't want Jacobi fields on my surfaces? Well, because when you have Jacobi fields, you could have a situation where you have, for example, an example for a picture you to keep in mind is a cylinder. So in a cylinder, well, round cylinder, all these surfaces here, they're stable. These transversal surfaces, right? And there is infinitely many of them. Okay, so there is like a degenerate family of minimal surfaces. But in the bumpy metric, it would be more, all of these would be actually more like this. And then there is just one. So it's like this degenerate family just only becomes one. Now, why can we make this assumption, without losing generality in our theorem? Well, because by a result of Bryant-White, the bumpy metrics, they are dense. So in other words, if I have a metric that happens to have like a cylindrical piece with these infinitely many minimal surfaces there, this would be a technical nightmare for me, because which one I would choose to cut, right? Well, there is a metric sufficiently close to it where that does not have these families of minimal surfaces. So it would have just one. And then in this case, it's just easier to know at which surface to cut. Okay, so we'll cut the manifold along closed minimal surfaces. So we got to find them. Now I'm going to define the properties that I want my components to have. So I'm going to say that a manifold with no empty boundary is geometrically prime if it has no embedded minimal surface in its interior. Okay, no closed embedded minimal surfaces in its interior. When I look at the boundary components, well, they're good. There is one of them which is either mean convex or is a minimal surface of index 1. And all the other boundary components are stable minimal true spheres. Okay, so manifolded boundary, all boundary components are stable minimal true spheres, except maybe one, which is either a minimal surface of index 1 or it's a mean convex surface. Okay, so the theorem is that if we have a manifold with a bumpy metric of positive scalar curvature, then we can find a finite list of surfaces such that they all have genus at most 2. And moreover, when I remove them from M, so M minus their all these surfaces, it's a disjoint union of geometrically prime regions. So they will have these properties here that we want. Okay. Right. So this is somehow where we start, because we will have smallness for all these bounded components. And then basically the proof of theorem A will amount to show that given a geometrically prime region, we can propagate the bounds from the boundary to a singular foliation to the interior of the geometrically prime region. Okay, so how this is done? So, well, this is a statement about the existence of minimal surfaces. And there's two kinds of minimal surfaces here. Some are they're stable ones, and the others, which are the index ones. So we're going to have to use methods for showing existence theory of these minimal surfaces. Now, the methods that we're going to use are going to be, can be a little different in nature. So sometimes you have methods that produce stable minimal surfaces. So in other words, minimization methods. But to produce an index 1, minimal surface, we need this procedure is called a min-max procedure. So let's go into this discussion. Okay, so the result that we're going to use, it's this result by Ketover, Lyukmovich, and Song, that a spherical space form other than RP3 with a generic metric, or the generic is just a generic name for bumpy, admits an index 1 minimal surface which is isotopic to the smallest Hagar splitting of M. So remember, a manifold with positive scalar curvature, we know its topology. It's the connected sum of a bunch of spherical space forms, right? And with S3 and then S2 cross S1s. Now, in those, so the first thing that we'll do is we'll basically try to look for those connected sums and then cut out those spheres, okay, and which are stable. And then what we have left should be spherical space forms, okay, with boundary components, which are these spheres, right? But this theory of developed by Ketover, Lyukmovich, and Song should tell us that there exists an index 1 minimal surface isotopic to the Hagar splitting of that spherical space form. And spherical space forms, they have Hagar splitting with genus at most 2. So there is this problem of having the stable boundary, but it turns out that in their theory, they have a local min-max theory that allows to extend this existence of index 1 minimal surface isotopic to the Hagar splitting for manifolds that have boundary. Here, strictly stable boundary, but that's okay because we are working with bumpy, so stability becomes strict stability. So in other words, a stable surface has positive eigenvalue for that operator. In our sense, it cannot be eigenvalue equals 0, okay? Because that eigenvalue equals 0 would mean that 0 is an eigenvalue. So in other words, we have a Jacobi field. But in the sense of bumpy metrics, we can't have that. So, okay, so let's see how we go about this. So let's say this is our manifold. And then first we're going to consider maximally disjoint family of minimal S2s, stable minimal S2s. So we're just going to look at all stable minimal S2s, okay? And we're going to look at the biggest family we can find, which is disjoint. And now we're going to have all these pieces that are manifolds with a stable S2S boundary, and they have to be essentially spherical space forms. So in each of these, I'm going to take the Hagar splitting, which has a genus at most 2, and I'm going to isotope that to index 1 minimal surface. Okay, so maybe here I get a torus on this bit. Here, if I apply this min-max theory here, I get another torus here, 1, 2. Maybe here in the middle, I get a genus 2 surface. There could be a possibility where I get another sphere. That's allowed. So this would be a stable sphere, and then here this would be a sphere of index 1. That's not a problem, and so on. So essentially, we are by finding these minimal surfaces, we are somehow recollecting the topology of the manifold into disconnected sums and this spherical space form, and then splitting it up like this. Okay. Okay, so with manifold like that, then we have all these geometrically prime regions. So they have this one, this one, this one, this one here, and then obviously on the other sides as well. Okay, so how then we propagate the geometric information from this geometrically prime regions to the interior, from the boundary to the interior? So first I want to discuss propagating area bounds, okay? And the tool for that would be mean curvature flow. So I just grabbed one geometrically prime region from a manifold that we're interested in. And it has this component S1 and then these smaller components, right, which are the stable minimal spheres. I call this one the large component just because it's the one that it's not the sphere, and it has index 1. So basically what we'll do is we're going to start flowing this guy by mean curvature. But Davi, this guy here, S1, is a minimal surface. So if I flow by mean curvature, it just stays put, right? Yes, but because it's an unstable minimal surface, what we can do is we can perturb it a little bit inside, then it becomes mean convex. And then we can start flowing by mean curvature, and we're going to get a mean curvature flow, which is mean convex. And that's very, very nice. And because there's a lot that is known about it. And basically, it's perfect for us for finding foliation because convex flow, it's a monotone flow. In other words, it flows out of here, right? And the solution is nested. It always goes inside. It's monotone. Okay. So basically, then let's assume that we want to now we have area bounds for S1, we have area bounds for S2, S3, S4, right? Because they are minimums that are S1 is index 1 and S2, S3, S4 are stable. And let's say that we want to foliate now this region with surfaces bounded there. And let me show you how to do that using the project. So we're going to forget about the diameter for now. All right. So one thing that can happen in the flow is that similarities can form. It's not a smooth flow for all time, and then we have to decide whether what kind of weak theory we want. So we could want like a big flow surgeries, we could want like level set flow, and so on. There's a few possibilities. So what we do is let me discuss how similarity can form. So basically, in the microfluid surgery, what I'm going to do is I'm going to choose some parameters such that when I'm flowing my surface, flow, whenever my curvature, my mean curvature gets too big, you know that's bad. That's probably just going to keep getting bigger and bigger. You're going to explode form some theorem. So I choose a parameter such that whenever my curvature goes above that threshold, I'm going to go to my manifold. I'm going to look at the regions which have like very big curvature, and I'm going to cut them, and I'm going to paste these spherical caps. And basically, what I'm going to do is when I do that, so for this picture, well, there is still a region here that which was this small here, that has a lot of curvature, so I'm going to discard them away. So essentially, my flow now is going to be these two pieces. Okay. Okay. So how this is can be formalized, I'm going to say that in the slide, you know, how one chooses this thresholds. But right off the bat, I'm going to tell you that there is a small problem here because we want to find the foliation of M. We want to, you know, the map has to be from the whole manifold to the graph. And this picture here is kind of showing you how the graph splits, right? So I have here a sequence of surfaces, but then after a while, I'm going to split. So this is like an edge, like a vertex forming, like one edge coming in and two edges coming out. This guy here, this guy here. But when I discard a region, this is going to be part of the manifold that I'm gonna that I'm throwing away from. So, but I still gotta define from this to there. So you see, so mean curvature flow of surface alone, because it discards some small part, it's gonna give it would give me a foliation of the manifold minus some very small pieces. Okay, so we gotta do something about those pieces. The good thing about them is that because they come out of the procedure where we are, you know, in regions where we know a lot about the geometry, uh, we know that these are small, and for instance, we can say that they're going to be containing small balls, which we can basically define a foliation of that by hand. That's sort of how we deal with small regions. Okay, so that's about the precise definition of surgery process. So basically what we're going to do is we're going to choose these curvature scales and trigger the neck and the thick. Okay, and the mean curvature is always going to be less equal than the trigger. And the surgery is going to have precisely where, at the times when there is a point for which the mean curvature becomes equal. So whenever that happens, I'm going to look at X, and I'm gonna replace them by caps, right? And basically, I'm gonna look at I'm gonna discard then the regions where the mean curvature is bigger than thick. So, for example, here, uh, once I replace the neck by these caps, I get 3 components. But here I have a component where the curvature here is in the scale of the neck, right? So in this component, everywhere this curvature is bigger than the thick. So I'm going to just throw it away. Okay. Here, well, here I have points. This component I have points where the mean curvature is very large, like the neck scale. But I also have ones where it's smaller, so that's a thick. So this component I keep. Same thing for the above component. Okay, it's only the components where bigger than thick everywhere that's thrown away. And that's why I know a lot about those components, and I can take care of them. Okay, so basically then what we're going to do with our flow is we're going to start flowing, okay? And we'll say, okay, Davi, but what is going to be the long-term process here? Well, for that, I'm going to use the level set flow. So mean convex level set flow in a situation like this will actually give me a foliation of this region, okay? And one can show that the long time behavior of that flow is that it has to converge to stable minimal surfaces. So this was a result by Brian White, which is a pioneered mean convex level set flow. So basically what will happen is that I'm going to start flowing, but now I'm not going to look at surgeries. I'm just looking at another formulation of this will flow, and it's going to foliate the whole manifold. It's going to pass through every single point, okay? And in the long term, it's going to converge to stable minimal surfaces. But we know that there is none of those inside of them. So they're going to have to be these boundary components, essentially. So, and Davi, but what is the connection of that with the mean curvature flow surgeries? Well, it turns out that if I choose the surgery parameters large enough, so if I take a sequence of surgery parameters large and large, so in other words, if I wait more and more to do the surgery, the mean curvature flow is going to be close to the level set flow in the Gromov-Hausdorff sense. So in other words, this is telling me actually that these regions that I'm discarding here, if I add all the areas, it's going to be small, actually small. So because you see the level set flow covers all the points, and the mean curvature flow is this with surgeries is discarding some of the points, but they have to be close in some Gromov-Hausdorff sense. So it means that whatever is being discarded has to have small total volume. And moreover, this is also telling me that the mean curvature flow surgeries eventually has to get close to these stable surfaces here. Okay. So what that will do for me is that because mean convex, mean curvature flow, well, the area of a mean curvature flow is always going down, even after surgeries. So what this is telling me is that I had the area bound for this guy, then I start flowing. So I get a foliation, right, of almost all this region here, where every single component has area less or equal than the area of S1. So it's a foliation with small area. Okay, now, again, I have to do something about the small areas, but I claim you do that by hand. So in the end, what you get is you get a map from this geometrically prime region to a graph where the pre-image of every point, it's going to correspond to a connected component up top, and it's going to have bounded area. So that's how you propagate area. Now, there is a problem here, which is that we really have no control of diameter under this flow. So if we also want to control the diameter, we'll have to do something about this. We have to modify this a little bit. So it can happen. It's actually very likely that this is going to start flowing. So the area goes down, but maybe there is a part of the surface that starts to go in the region of the manifold. And then once you go more and more and the surface starts to get, the diameter starts to, increase, and maybe it's going to violate the bound that you wanted to prove, right? So we'll do that, something about that. And I'm going to discuss that in the next video. Thank you.